Hi guys, I'd like to start. I was told that I would have a midterm, did not even two. So what I'll do in this class is to three questions on the midterm, right? So surely I understand that. So when they eventually get even midterm, you're in good stand, right? So the next time we meet, um, I think so we'll have started like inductance and stuff, and it should be on the reluctance by now. So I'll go through that. The last thing we probably will do is the three-phase. Three-phase systems is right. It's not difficult at all. Right. You just have to know the different types of formations and the equations. That's it. Right, but anyway, to start, right? So if at any point if you have any questions, you can always stop and ask. Right. So feel free. Right. So this one, a material high reluctance. So remember, anytime you see reluctance, you can think of it as resistance, right? But have less flux, and same thing with flux. When you think about flux, think about it like current, right? Passing through a material with low reluctance, if you see on this MMF, think of it as voltage. Yeah? So it's easier to conceptualize in your brain, right? So they're trying to say a material with higher resistance. Think about it. A material with higher resistance will have less current flowing through it than a material with less resistance if the same voltage is applied to both material. And that makes sense, yeah? Because V is equal to IR. So if I try to make current, it's something by the formula, yeah? So if I increase the resistance, I'll be decreasing the current, yeah? And by vice versa, if I decrease the resistance, I'll be increasing the current. Yeah, so the answer is true, and that makes sense. Right, and applying it to replace it with reluctance and stuff is the same idea. So anytime you're doing a question, anytime they remove reluctance and flux and magnetomotive force confusion, just replace it with resistance, current, and voltage, and you should be able to at least conceptualize it due to previous knowledge of electric circuits. Right? That's all that was. Number two, magnetic moments are due to orbital spin of the electrons around the nucleus. Not all the time. Alright, a magnetic moment is it's similar to dipoles. So like if you have a material, you will have domains, and each domain it have a grouping of dipoles that oriented in a particular direction. Yeah. So the moments is literally going deeper into the dipoles and magnetic moment, right? So it isn't only caused by the orbital spin of the electrons. Yeah, it could be caused by the magnetic field. Yeah, and all external factors or internal factors. It's not only the key word here that spell it out is only. Anytime you're doing a multiple choice exam, the word only is a very strong word to use. Majority of the time, unless it be an explicitly obvious, the answer is false. Because only is a very strong word to use in a multiple choice exam, especially when it's true and false. Yeah. So if you cannot think of any others, most of the time the answer is false. Yeah. But this one was not one of the exceptions. All right. All right. Question three. All right. The amount of flux. So hopefully you all know what flux is, right? So flux is the lines, the material, yeah, that go in a particular direction. Yeah. So when all these dipoles say in these domains are aligned in the same direction, yeah, they cause an increase in the flux or the magnetic field inside the material. Yeah, think of it as like an army when everybody faces the same direction and shooting in the same direction. Yeah, you get more bullets flying in the same direction. And by extension, a stronger attacking force. Yeah, so the flux, when all the dipoles and the domains align in the same direction, and most of the time they align, almost all the time, they align in the direction of the external magnetic field. Right, so if you put this material in an external magnetic field, and let's say it's going in this direction, the dipoles will all align in the direction of that external magnetic field. All of them. Once the magnetic field is left on for a long period of time, after a period of time, all the dipoles, all the moments, all the domains will align in the same direction. And because of this, you will have an increase in the magnetic field inside the core, and it will be very strong and very high compared to the magnetic field outside of the core. Yeah, because outside it going through air and inside it going through a very conductive material with respect to flux. Yeah, so go through. So the amount of flux going through the loops of a coil, that is flux density. Yeah, the amount of flux passing through the loops is flux. From the time they say coil, they're talking about the flux density. Right? Flux density is just the area divided by the amount of flux you have. So we know that is BA. Yeah, so if I make B the subject of the formula, which is flux density, you will add the flux divided by the area because it's flux density. Yeah, and I say I get flux density. So the amount of flux lines divided by the area across which it passes. Yeah, so that's this one. The constant proportionality between the driving force, which is at the MMF, and the flux, so that reluctance. This fancy in the same driving force. It's just MMF, so like confuse you. And flux. So back to me brain again, see? Know your equations, because the equation that popping out in my brain is F is equal to phi R. Yeah, because MMF and phi, the equation that link the two together is this here. So they said if I make R the subject of the formula. Yeah, so reluctance will be the constant proportionality. Yeah, here with the plot a graph, F and phi, find the gradients, we'll give you R. That's looking familiar because it's the same thing you used to do in physics. When you use any Ohm's law, V is equal to IR, and you have V and I, and you draw the graph of V and I, and that's define the resistance, and it was like, oh, if I find the gradients, that will give me resistance. Yeah, same thing. You're just thinking about it in the magnetic domain. Yeah? So that's all that was. Right, and the flux linkage in a coil per ampere of current flow. Right, there's inductance. Yeah, there's inductance one thing. Yeah. So I think L is for inductance, lambda and I. Yeah, so this the equation for inductance. Yeah, so this here is the flux linkage. All this in the formula sheet, right? And what I is the current. Yeah, so the flux linkage per ampere of current, that is inductance, right? If take this into your life in maths, anytime you hear per means there's a fraction involved. So whatever they say before, think of this as the bar and ampere. So even if I didn't know, I could have formed the equation one time. And that's like I said before in this course, you need to know your equation. If you don't know equations, you'll struggle a lot. Trust me. All right. So by now you're in master them little equations. Make sure I'm good. Anyway, so the best, which best describe the phenomenon of ferromagnetism. Right. So ferro, iron, and magnetism is well North Pole, South Pole, the flux are aligned in the direction. Yeah. So the name given to the property of certain materials whose atoms are arranged in such a manner that their magnetic moments supplement one another. Right. So what I mean by this, we could go back to the same thing I drew here, right? This material that I drew here, it's have different type of material, and you can always Google it, right? It's a ferro, it's have I think it's have others, have three, but the most popular one they use for this is ferro, right? What ferro means, it has some magnetic material that once you put it in a magnetic field, all the domains will align. And if you remove that magnetic field, it will just stay aligned. Yeah, and it will just stay a permanent magnet forever. But some materials, when you remove that magnetic field, they lose some magnetism. And we know how it loses some magnetism because some domains go back to being unaligned but some of them stay in one direction. And once you have domains that in the same direction, they will have some magnetism being left behind. Yeah, retentivity, the hysteresis curve, right? From when you did the hysteresis curve, when it went back, it then go back to zero, it cut the y-axis. And because it cut the y-axis, it had some magnetism being left behind. Yeah, and that basically giving you the magnetism that left behind. So ferromagnetism, the domains are aligned when the magnetic field is there, or when you remove the external magnetic field, some of the magnetism will stay aligned, some of them will go back to be an anomaly, right? So that is literally about ferromagnets, magnet fields, right? So supplements, they will supplement each other. Supplement meaning they aid each other. So when they all align, they aid each other. Yeah, so those type of materials, they can hold magnetism, right? Parallel manner, but that's the name shall not. The name given to certain materials whose atoms are arranged in got nothing to do with parallel manner. Yeah, it can't be the net magnetic moment is zero. Why? Because you wouldn't have any magnetism. Yeah. So if, like you say, I had a do, that's kind of deep. If this pointed in this direction, 1, 2, 3, 4, 1, 2, 3. If they face in this way, right? And they face in this way, and mathematically they will sum together and give you zero, which means that they have no magnetism. It's like a rock, a big stone. Yeah, it have no magnetism. They have no domains aligned in the same direction, and that is what creates magnetism. If you don't have that, you have no magnetism. So it can't be this. Alright, so original direction and the application enable the pursues the means what opposed to it not really means, right? So the unison that's correct here is this one. They supplement one another. Yeah. Right. Number 5. If a sinusoidal current is applied to a coil wrapped around a ferromagnetic material, what causes the flux to concentrate on the outer edges of the coil? Alright, so I'll show this. I'll show you this in a right. Right. So by introducing you all to this, right? Before we were talking about ideal situations. What I mean by that is the flux inside here, they all they are uniform, meaning they're just perfect. All of them going across straight line, perfect, perfect, perfect. It don't matter where I calculate the flux density across this material, it will always be constant. But that is an ideal situations, and it's not how it is realistically. Realistically, this is how it is, right? So you have the same material, but what happens to the flux is that the fluxes tend to concentrate on the outer edges of the material. So if you calculate the flux density on the outer edges, it will be higher. And as you continue to go deeper inside the material, it will decrease. So it will look something like this. So majority of it will kind of like concentrate on the outer edges, like a lot. Same thing for this side. And like as you continue to go in the center, it's not a lot, but it's kind of look like it bending. Yeah, so this is really how the fluxes flow in the material, right? Yeah, and this phenomenon is called the magnetic skin. Skin, meaning it literally concentrated on the outsides of the material. Yeah, and little flux flows in the center. That's saying none, but majority of it is concentrated on the outer edges of the material. Yeah, and this is how flux realistically flows in the material. But for calculation purposes and for your understanding purposes, they just tell you assume uniform flux density. Now we understand why students tell you assume uniform flux density. Because in a realistic situation, this is how the fluxes flow. It has concentrated on the outer edges of the material. Meaning the flux density on the outer edges higher than the flux density going closer in, as you can clearly see. But look at space in the inside here. As you go out, it kind of gets thinner, get more concentrated. Yeah. So that's called the magnetic skin effect. lattice. The phenomena where the flux density is concentrated at the outer edges of the core material. Yeah? So hope that helps. Alright. So number 6. For the magnetization of a ferromagnetic material, the flux density lags behind the magnetic field intensity. Alright, yeah, this is hysteresis, right? For those that forget what hysteresis is, let me just run through it quick. Alright, so let's draw a little domain here. So like I said, this is my, you know why I'm not gonna draw so much very relevant to you. I'm gonna just take 2 domains, right? Obviously, in our realistic material, it have billions of domains. Yeah, so that's gone, right? Okay. So let me say initially, this is how we mark thing look. The domains all over the place, it's not magnetized, everything started poof. Yeah, meaning it's not from 0. So the hysteresis curve come from something called the BH curve. Yeah, so nice. So let's say we connect a battery. Let's say we just connect a battery. Right? So positive, minus. So when you run the current through this, it would generate a magnetic field, right? So the magnetic field, let us say generate that. Yeah? So let's say the magnetic field going in this direction. Okay? So let's say you had a switch. The moment I put on the switch, the magnetic field will generate. And it will increase up to a maximum value. Yeah, because the material, all the losses and stuff, the magnetic field will just increase up to infinity. It will go up and stop at that point. In simple terms, the flux lines, the amount of flux lines will keep on increasing. So it'll go from 3 flux lines, 5 flux lines, 10 flux lines, 15 flux lines, and it will just stop at 20 flux lines. Yeah? So that process of increasing H, it will also increase B, because B is equal to mu H. So if I increase H, I'll increase B. Right? And also H is equal to Ni on L. Right? L is a constant because the material is not changing. And as a constant, like my coil, my goodness. Let's draw my coil. Because the ferromagnetic material had to be wrapped around the coil, right? Right. Yeah. So if I increase I will also increase H. So let's keep these 2 equations in the back of your mind, right? So let's say we start from 0. The moment I put on the switch, the magnetic field will start to increase, meaning H will start to increase. Because H is increasing, B will also increase, right? So you'll get something going up like that. But we know, and as I just explained here, this H will be limited. Why this H will be limited? Because I is limited. Because I is directly proportional to H. When I reaches a maximum plane, is a circuit, the current will be fixed at a point, right? So the current will increase to 3 because this current will up and stop at a value. H will also stop at a value because they are proportional to each other, right? So when H reaches a max, let's say H max is here, at that point, B will saturate, meaning it cannot increase past that point. Yeah? And in the physical domain, in this part here, these domains, it means that all these domains here are aligned in the same direction. Yeah? It literally reach a point where it cannot be magnetized anymore. Yeah? So it reach a point of saturation. Everything will just saturate. So this point here, we call it B sat. That B sat is pictured as all the magnetic domains in the material, they're in the same direction. All of them, every last one of them. At that point, you can't get any stronger in terms of your magnetic field inside the material. Yeah? So it don't matter how much you increase that current after that point, and how much you increase the H, how much you add more turns, like you do whatever you want. Them damn domains, they're already aligned. It have no more to align. So because you have no more domains to align, it cannot get any more magnetic field out of it. So it saturates. B saturates. Can't change it. Fact. Yeah, if you change the core material that is probably bigger, yeah, you could probably get more, but you're not gonna do that. Yeah, because it's one material to use, so it's saturated. So at that point, right, what will happen is, let's say we were to decrease the current. Yeah, somehow we decreasing the current. If the other rail starts or something like that, say we decrease the current, right? So when we decrease the current, let's say the current is 3 amps now, flat at 3 amps. Yeah, so we can't change. If we were to decrease this, it will decrease from 3 amps to 0 amps. Yeah, so because this I goes to 0, H will go to 0. Yeah, and if H go into 0, B will go to 0. Wrong. Yeah, B will not go to 0. Why? Because some of the domains will stay aligned with the magnetic field, and it will just stay aligned. Even the magnetic field not there at all, some domains will still be aligned. So therefore, the core itself will generate like a weak magnetic field of its own. Yeah. So what happens is, from here, you decrease the current, you decrease the current, you decrease the current, H becomes 0, meaning you have no external magnetic field, but some of the domains will still be aligned in the same direction. And because of that, you will still have some retained magnetic field in the material. And this point here is called the retentivity point, or the pointer is called retentivity effect. Yeah, even if you remove the external magnetic field, the core will still maintain some magnetism. Yeah, so remember we are 0 amps now, right? So how we could get this leftover magnetism to be removed? We could just continue decreasing it. That makes sense. If you continue decreasing it, it will reach 0. It will just lag. Hey, look the word, it lagging behind. Yeah, when one reach 0, he's still high. When he continue, you now reach 0. Yeah, it's like playing a game with a man. Like, yeah, you done pass the building and he done, hey, with the building is by, and you just shoot the yeah, he lagging behind. When you reach, he behind it. When you finish, he's still coming there, that lagging behind. So when this H is 0, B still there, retain it. So if I continue to decrease this current, so let's say I decrease it to -2. Yeah, so when there's -2, H will be a negative. All that will look like in the physical domain is that these directions are the magnetic field lines here. It will just reverse direction. Yeah, that is what will happen when you go in the negative direction. Everything will just reverse. Yeah, and this will be a minus here, and this will be a plus. Everything reverse. Yeah. So now the magnetic field, the domains will kind of be forced to go back in the opposite direction. So cause it to restructure itself, right? So because of that, if I continue, I add this -2. As I continue to go from 0 to -2, the B will decrease. And I will finally have my B being 0. Yeah, but the H is not 0. Sadly. Yeah. So at that point there now, I finally reach 0. At this point here, let's say we were to continue to increase, or sorry, decrease the current, the same thing would have happened, but in the opposite direction. It's just now we're not starting from 0. So if I were to continue to decrease this current, as you decrease the current, you will decrease the magnetic field. And if you decrease H, you decrease B. In layman's term, the same thing happened when it was going in the forward direction as what happened in the reverse direction, but in the opposite direction. So in another way, if I increase H, I will increase B. But the same thing happened in the opposite direction, meaning that everything reversed. The magnetic field is now reversed. Yeah? So in this direction now, the magnetic field is still on. So therefore, after a long period of time, all the domains that were initially in the opposite direction will now align to be in this direction after a long period of time. So the same thing will happen here again. It will go up and it will saturate. Yeah, so there's B sat, and the negative, so you can say is minus B sat. Yeah, just like we did before. So like we say it's saturated at -3. That's to keep the uniformity, right? So now, if we were to decrease the current to 0, same thing will happen again. You will just go, but we know it will not go back to 0. It will retain some magnetism. Yeah? So it has 0 now. What can we do to go back to the x-axis? In this case, we add a reverse current. In this case, we increase it. So let's say we increase it back to 3. In physical terms, these lines here will be reversed. And because I reverse it, the domains will be like, oh, shimps, I'm in the wrong direction. and it will take a long while for all of them. So at this point here, the domains that weren't aligned, it will go back. So now we'll just go back to being here. So at this point here, just like here, they're all over the place, they're scattered. Yeah, and if you continue with this magnetic field here, the same pattern will happen again as you continue to increase it. Same thing will happen. Go up to the V-sacks and you reverse the current, you retain some. If you continue to reverse the current, you reach a point where you have no magnetism. And then if you continue, you will increase up to minus V-sacks. And then if you reverse the current again, you will go back. And it's the same thing happening over and 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 over. Yeah, and this is why that's called the hysteresis loop, hysteresis curve, whatever you want to call it. Yeah, so in a normal operation, this DC source is an AC source, right? And if you understand the DC, you can understand the AC. Because the AC they can change in like with frequency. So this here happening very fast. Yeah, hundreds of them happening. So every time, like in one oscillation, you might have 3/4 of one of these loops here. Yeah, and as it continues to go over and over and over and over, you can see that it will continue changing. But the point you need to catch from this is that it will never reach back to zero. If you notice, it never reached back to zero, ever. Once it started, it will never reach back to zero. Because in realistic operation, the material will have some resemblance of some magnetism. At least two domains will be aligned to each other. Remember, there's millions of them. No way a million domains not aligned, or at least some of them not aligned in the same direction. Yeah, so that is the hysteresis, right? So hopefully you catch it. All right, and obviously, yes, and that is hysteresis. As you can clearly see, the B and the H, it lags each other. Yeah, so the flux density B, it lags the intensity. As you can clearly so. When H was 0, B was still going in the direction to be 0. Yeah, so H was 0 here, B was 0 here. Yeah, so the B lagging behind the H. Yeah, that idea is right. All right, so number 7. This one, it has rubbed many wrong way. But you gotta use the right hand grip rule. Yeah, so you see that dot here, and you see the X. All right, so remember it's coming out, this going in. So X means it going into the paper, and O means it coming out. Yeah, so if you use your right hand grip rule and you point your thumb in the direction like going in, your fingers will curl in the direction of the feet lines that you see it. Yeah, or you could think of it as a wire wrapping around. So I'm gonna draw. Yeah, so you can look at it like that. And the wire itself have a magnetic field of its own. Yeah, a curl in the wire itself. Right, and if you put this wire inside the magnetic field, due to Faraday's law, when a wire current conductor is placed in a magnetic field, it will generate a voltage. Yeah, so when that happens, the south pole will go in this direction, right? So the flux will go from north to south. This will be the north here, and this will be the south. That is all again. Right? That's all. Nice. Number 8, eddy currents. Right? So eddy currents is circulating currents in the core material, right? So it's literally like these things. It's like circulating currents. Right? These circulating currents are caused by the direction of the current continuously changing direction. Yeah, so you really only see eddy currents in AC, but mostly in AC poles. Why? Because it'll look like this. Remember this happened in real path, right? And one time it's going in this direction. The next time it might be going in this direction. Yeah. So after that happened over and over, after the majority correct. So the current lines are the same as you can so you can see that. So one time it go in this direction, and the next it go in this. That happening so fast that you will have circulating currents because the electrons will always be, it's like a chasing. You're lagging so far behind it, you're like chasing. So one time it's going forward, next time it's going back. So you're constantly jumping on a forward and a back motion continuously. So what will happen is you will just end up just going around in a loop. Yeah? And because of that loop, you have eddy currents. It's called circulating currents in a core material, right? And I think I sent a picture in the chat with the equation for eddy currents. So at low frequencies, you wouldn't have that much eddy currents because the direction changing so slowly that the electrons could just go in one direction and have time to realize that change and go back. Yeah, you wouldn't have as much eddy current or eddy loops. Yeah, but as you increase the frequency up, the, the direction will be changing so fast that you'll have more induced eddy currents in the core material. Yeah, and by extension, if you have a thicker core, it means you have more space for more circles. Simple terms. So if you have more space for more circles, you will get more eddy currents. Yeah, so it's a whole equation, right? So I send the equation there, so it's good to keep in mind. So like if sir was to tell you if you decrease the frequency, what happens? The eddy currents from this, if you decrease the frequency, the direction not changing as fast, so therefore you have less eddy current loops, and there's a nice equation to keep in mind. Yeah, and that's eddy currents. Yeah, right. Okay, this one is. The question was, in which of the following scenarios describe which we expect to get a sustained zero reading on a voltmeter? So basically, the asking here, in which of these you will have zero here? Yeah, and we know about Faraday's law. Even if you to get an induced voltage in a coil, because you can clearly see these coils are not touching. So there's mutual inductance going on here, meaning the magnetic field induced from one coil is causing a voltage to be induced in a other coil. Yeah. So Faraday's law states when the coil change in the magnetic field, key would it be the magnetic field changing, right? When that goes through a coil, a voltage is induced. Yeah, so let's keep that in mind. You need a change, you need a coil, and you need a magnetic field. Yeah, keep those three things in mind. Very good. Applying a high frequency square wave DC signal across coil one, right? So square wave like this. Right, so that's right. Yeah, so if you apply a square wave like this, right, we can clearly see one, we have a change. Because 1 minute at plus and at minus. Yes, we can clearly see that it is changing. Yeah, so 1 minute, it's a change, right? So once you have a change, you will have a voltage because we had the coil already, so just check. Yeah, and because of the change, when you pass a current through a coil, it will generate a magnetic field. It mightn't be as perfect as you think it will be because it is a square wave. But because you have current flowing in the coil, you will have a magnetic field. Yes, it may be flat, it doesn't mean it'll be 3 volts for a long period of time, and it would drastically change. It would drop to -3. So the magnetic field will kind of be kind of rigid, but it is changing direction in the coil, and it is creating a magnetic field. So because of that, you will get a voltage here, because Faraday's law is complete. So this here it comes. If you apply AC voltage to coil one, well, so that is perfect. Everything nice. So we have a change. Yeah. So you have a change. This one here. If I apply a coil one, you should get a voltage. Yeah? Because remember, each direction does switch constantly. And if it's switching constantly, you have a voltage being induced in the coil. Yeah? So this one, don't think so. So this one here can be this one. Right? Because that one will give you a sustained DC, a sustained voltage, non-zero voltage. The same non-zero is zero. Let me make sure I read the question properly. I think I'm misinterpreting the question. Which are the following? Okay, this is non-zero read. Oh, non-zero. Okay, meaning that is not zero. But let's go back to it. Okay, basically asking which one will generate a voltage. All right, now catch what I asked. So it is never zero, it's non-zero, right? So yes, this one here can't be this one. Applying a steady DC to coil one and continuously moving the coil back and forth. Yeah, it basically looking like this. If you generate the flux, instead of the current changing will cause the magnetic field to change direction, you can literally physically move the coil back and forth or side to side. Yeah, because remember, you just changing this. So like if you had the flux cut in the coil, it have a million ways where you could actually change how many flux cut in the coil. Because that is what will induce the voltage. I can either move the coil back and forth, that will change the magnetic field cutting it. I can move it side to side, that will change it. Or I could add a AC, meaning the direction of the magnetic field would literally just change direction continuously. Yeah? So all that could induce a voltage because you are changing something. Once you have a change and a coil and a magnetic field, you'll get a voltage, right? So start applying a DC to coil one and move it back and forth simultaneously. Okay, at the same time. Okay, so that means like this whole page, think of this whole page, and they say DC. So basically, DC means that the magnetic field is not going to change direction, right? Meaning not going to change the polarity. Meaning if it's going this way, that's going to stay so. So they basically saying if I hold the four corners of the page and I literally just move it back and forth, they're not going to generate a voltage because the flux cut in the coil not changing. One of the coils had to be stationary and the other one had to move to cut for the flux changes to cut. Yeah, if both of them moving simultaneously, nothing going to change. It's like you saying in a car next to somebody holding the hand at the driver and all they're moving. It's like all they're moving at the same speed in the same direction, nothing changing. But if was both y'all were in separate cars and somebody push out the hand and hold the next man hand through our next car and our next man move with reference to you, your hand will be pulled and that is what you're looking for. But if both of them move in the same direction at the same speed, nothing changing, they're not going to generate a voltage. Yeah? And we'll apply an DC, well, that's the goal. If you just apply a DC, it just going to stay just so, nothing going to happen. Yeah? The flux is cutting the coil, but it needs to change. If it's not changing, you can't get no voltage. Yeah? As I was saying, you need to change the coil and the magnetic field. Yeah? So the answer for this one was these two. Yeah, applying a high frequency square wave DC, I'm assuming what I mean by the square wave is this one. Since that wasn't the answer, that the square wave probably look like this. So that's just pulsating. So you're just going like this, like that, and not going to the negative side. Majority of it so you can see. Yeah, so it's not really changing direction. Yeah, it's just staying positive. Yeah, so this one here is contentious if you think about it deeply, because a high frequency square wave, because it's high frequency and it's DC, meaning it just stay in one direction. It, it's contentious. 'Cause I think when you were doing it in class, we had a whole debate about this one, because you can clearly see these pieces here. It is changing, but what's so sad is that this dropping, yeah, it literally just dropping from 1 to 0 so fast. So it not really seeing the change. Majority of the time, you probably don't go and see the one. Yeah. If you see this question come back, that's no it's two odds. The high frequency square wave one do that. Right? Anyway, so yeah, number 10, ampere circuit law states the line integral, HL is equal to Ni of the magnetic field intensity across a closed path is equal to the law can only, remember I tell you about this only thing? Yeah? Only be applied if a cross-sectional area of a conductor is not a normal path. Now, that's true. That and this only. Yeah? Is not normal. Perpendicular. Yeah? So, force one thing. Anytime I see them say only and stuff, that force will be blinking a man. Because only is a very strong word to use and normal. Yeah. This here is the literal definition of best circuit along with all the fancy words in it. I think it's in two slides. Yeah. But he will never ask it to define it. So there's no how to apply it. Right? Anyway, which of the following is true about eddy currents? I think we just did eddy current, right? A high frequency applied current will increase. Yeah, it will increase it as I show you. Yeah. Eddy currents as well, yeah, I just tell it. Eddy currents will to increase. Nah, it will increase to it will move to that. It will actually decrease the flux density. Yeah, because I'll put everything together now, right? Remember the magnetic skin effect, the flux was outside the material, right? Majority of it, the flux density was outside, right? Eddy currents, most of the time are generated in the center, right? Yeah, these loops. And look at that, everything come full circle. Now you're actually seeing one, remember this, right? If I have a line going in this direction, right? And let me say my eddy currents flowing in this direction. And these two are together to give you zero. You know, the cone. Yeah? Because plus and minus. If you put those two together, it will cancel each other. Yeah? Superposition, destructive, constructive. Yeah? So if both of them were to be in opposing directions, they will cancel each other. Yeah? So putting everything together, those eddy currents, it wouldn't, majority of the eddy currents, it would not aid the magnetic field. It will actually cancel out pieces of the magnetic field. Yeah? Remember, if the flux going in this direction, right? And it change in direction. So flux going here. Yeah, so majority of it will be cancelled out in the center. So literally adding into why majority of the flux is at the outer edges, right? So the eddy current will really increase. Yeah, it will increase it. Some may, but majority of it will cancel as like this. Yeah. So this one wrong one time. Because they say eddy current will to increase. They never say some, it could be a flat answer. So no. All right. Nice. Lower any frequency applied will lower the eddy currents, thereby increase flow. So that had nothing to do with the magnetic skin effect, right? And the magnetic skin effect is as a result of, yeah, I'll just show you that. You have the eddy currents in the center, some will cancel out, so you will notice in the center, it will be kind of thinner, and on the outer edges, you will have more of the flux being concentrated. Yeah? So that is what. All right, 12, the flux linkage in a coil. Then an EMS is induced in the coil, which of the following is the direction, right? So Faraday's law says if you have a change of magnetic field cut in a coil, you have a EMF being generated. Lenz's law says that the direction of the induced EMF will be such that oppose the change that causes. So they kind of work hand in hand. Yeah, so the Faraday's law telling you something gonna be induced. The Lenz law telling you what direction will it be induced. That's Lenz. Yeah, right hand grip rule is just like the direction of a magnetic field and a current carrying conductor, like a wire. Yeah, that is right hand. Ampere circuits are law, well, shit, I don't know to do the same. I'll make this. Now, Faraday's law does just tell you the EMF induced, but it doesn't tell you the direction. That Lenz. All right. When applying a sinusoidal magnetic field intensity to a ferromagnetic material, under steady state condition, the flux density in the material will never reach zero. Yeah, we just did that. It will never reach back zero. Yeah, the flux density B, it will never reach zero. Yeah, it will never reach zero. They will have some residue of the magnetic, or some residue of the magnetism being left behind when you remove the magnetic field. Yeah, we just did that, so it's true. We call it a residue or retentivity. Yeah, it retains some magnetism. All right, which of the following when an external magnetic field is applied to a ferromagnetic field, the alignment of the domains will remain. Nah, I can't be supplying an external magnetic field and my domains don't want to move. we know the domain is going to align with the external magnetic field. Yeah? The domain wall motion will occur when the magnetic domains that oppose the external will grow at it will. If you are opposing, how you gonna grow? You have to be in the same direction to grow. Yeah? The material will possibly become permanent magnet as a result of the overall magnetic moment becoming aligned. Yeah, that's beautiful. Yeah, it could become a permanent magnet. Yeah? Become when the domains are aligned and you remove that magnetic field, depending on the type of core it is, it could just stay aligned and it just become a permanent magnet. Yeah? Some materials, when you magnetize it and you remove the thing that magnetizes it, it will just go back to being non-magnetized. Some materials, when you magnetize it, remove the thing that magnetizes them, it will just remain magnetized. Yeah? Alright, remember this only thing I tell you about. Only the magnetic domains that are more or less aligned with the external. No. But the results, nah. The moment will remain unchanged. Yes, that's not. Actually, yeah, so that one is the answer. That only kind of just throw people off. Most of the time, the only answer is false. Yeah? Well, depending on the answer. All right, question 15. The figure below shows, I just showed you this. Yeah? So, with this one here, it didn't start from zero, which is really what happens. So, let me say it had a h. As you started increase h, remember this I, right? This I here. If you can see it properly, right? So as I increase I, h will increase. So that's what we're doing here, right? So that basically me just increasing my current and you reach up there, right? Yeah. So as you reach there now, basically you hit. Yeah, then you decrease the current, which is what you're seeing here. So when you decrease the current now, you reach here, which is here, which makes sense because if I is zero, H is zero. Yeah. But B will not be zero because of the retentivity effect. Yeah. So at A now, we add a back current, which is going in this direction now. So at that back current, a short period, only a piece of it, probably up to like here. At that point, your B will finally reach zero. But the H will be zero, as you clearly see, because the I is not zero, right? And if you continue to increase current in that direction, yeah, you will reach a max flux, which is basically B right here. And if you repeat the same process now, if you decrease the current, it will cut by 1 0. So yeah, here now, and you just repeat the same process. If you continue to increase it, probably after like right here, you will reach the zero mark. And you continue to increase and the same pattern will just happen over again. That's basically the hysteresis loop. Well, it is the hysteresis loop. Right? And that's all I'm going on. I think so he will like give you like letters and he wanted to like place it in the pieces. Yeah, so that's what went on. Yeah, but if you understand what's going on, you increase current, go up to max, you decrease your current, it will intercept the y-intercept. Then if you continue to decrease the current in that direction, your B will reach zero. Then if you continue to decrease it again, you'll reach a B sat in the minus direction. And if you decrease, in this case, if you increase the current back, you will go back to your continuous y-axis. And if you continue to increase the current, you'll reach zero. And if you continue to increase the current again, you reach a max, and the same pattern has happened over and over. And you can model it by a sign, but I literally what happened. All right. All right. Which formula the force on a conductor of length L in a magnetic field? Right. The F is equal to QVB. All right. Q is, I believe, a charge. V is the velocity. B is the flux density. So that's basically the force of a particle in a magnetic field. So this has nothing to do with the conductor. F is equal to HL, that is ampere circuital law, and our wire, is ampere circuital law. This here, Lorentz force, not Lenz, Lorentz force. F is equal to flux density, current, and L. Yeah, so F is equal to BIL sine theta. Yeah, so that is the answer right there. Can't be nothing else. Right, 17. Right, so the rest, self-explanatory, right? Because they doing it in class, but from what, okay, I think I introduced fringing to you all already. Yeah, so fringing is when you have the air gap, some flux will like leak outside, right? It will bulge outside. Some of it will bulge. Well, the majority will go through here, right? But some of it will like bulge outwards. And that outward bulging is where that's called fringing or the fringe effect. Yeah? So outer bulge or the magnetic flux in the air gap here, right? Would picture input, right? So, right, calculations, this one here, right? So you're just using this equation here. T is equal to NIAB. Yeah. So they already give you your N, they give you the diameter, so you could find E because it said there's a circle. So you could find E pi r squared. Yeah. They give you B for the flux density, and they give you I. So since they give you N, so T is equal to N, they give you N. They give you I, you can find E by pi r squared times E. And B, they already give you 0.9. Plug it in a calculator, get out. That one simple. Alright, that's all it was. Alright, 24 EMF to be induced in a coil due to a change in magnetic field. The induced EMF is given by the rate of change of flux. 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 That's all. That one some question. Yeah, that's the rate of change of flux. Yeah, that's all it is. Nice. Because of the density, that is why it becomes flux. Right? If that just leave it as flux, yeah. Right. Alright, I want to go to these BH curve. Alright, the volume or the area bounded by the BH curve or the hysteresis loop, it will give you the energy lost due to heating. Yeah, because constantly rearranging the moments, it will take energy to do that. And because it's an AC, that happening for plenty. And after a while, it will generate heat. Yeah, so if you have a wider pH curve, that means you'll have more energy losses. Yeah, so let's keep that in. All right, so these questions, oh, let's go. Let me go to the calculation for this. All right, and I think that's basically the heavy part. I'll go to the two calculation questions, and the rest is just repeats. So that's asking you different parts of it. Right? But once from the videos I did before, the calculation questions here is fairly simple. I went through them already. All right, so let's try this one. All right. The figure shows a coil, they give you N, wrapped around a plastic. Hey, this is plastic, right? So you don't have any relative permeability and right? You just use it music, right? Circular cross-sectional area. Right? So if you cut this in half, so the radius of the toroid is 30 centimeters and the diameter is 40. Without assuming uniform flux density of the coil, the current is 51, okay, they get I. They want you to calculate the flux in the core material, right? So, which is fairly simple. So if you want flux, right, you have multiple equations that you could use to get flux. Because it's a closed path, you could use ampere circuit. Even if it had an air gap, you'll just have to add the piece for the air gap, right? That's like I did in the previous question from a couple of weeks. So we could use a manipulation of this to get our answer. All right. So because of one flux, we could use Ni is equal to phi r because the one flux. Flux is this, right? So we could use Ni because we have N and we have I. We could say that is phi r because this is what we want, right? Yeah. So we could just transpose with one time. Ni on r. Yeah. So since we already have N and I, the only thing we don't have is R. So we just have to calculate R. Once we calculate R, we can get what we want, right? So R is equal to L on UA. Yeah, so that is where we go. So we need the length of, so we know it's the center. and they give you R, and they give you D. So basically, we want from here to here. Yeah, that's looking at it. You should be able to look at the material and know what the center piece is. So if you're looking at the maths now, they said, well, 30 and 45, right? So I believe, so you're saying that this is 30 and this 45, but that will make sense, right? 45 have the smaller piece inside, right? So that means this here is 15, right? Yeah, because 30 plus the piece outside here will give you a 45 on the outside piece. So half of 15 is 7.5, right? So therefore, this piece from here to here, it will be the 30 plus half of the 15, which is, so you get 37.5. Yeah, that's all our up. But from here to here, there's 45. And from here to here is 30. So if you like rotate it, right here will be 30. Yeah, and 30 plus 15 is 45. Yeah, so if you rotate it back now, this piece here is 15. So I want half of it to add to the 30. So that'll be 15 divided by 2, 7.5. Add it to the 30, and you get that. You get the 37.5, right? And because of that, we could get L. Yeah, because it's a circle circumference. You can get L. Yeah, 2 pi r. Yeah. So once you do a 2 pi r, you get L. Yeah, so I see. So what I did here, R, I already had the calculate the area, right? Once you calculate the area, so you have E here, which is this piece here. Yeah, the calculate L. So yeah, so we did get it to the 7.5. You convert it to centimeters, I think they gave you it in millimeters. Yeah, well, convert it to meters as a unit. Yeah, so keep working on SI units. Don't change them. So they convert it into meters. So L is 2 pi r, just like I said, you get your answer. For A, right? So let us go back. So I can show you how to get the A, right? So this piece is what I want, right? So since we know from here to here is 45, right? This piece here should be 15. So here is 15, right? So we need R. So we just need half of 15, right? Which is 7.5, right? Yeah. So if you convert that to what I have, you'll get 0.075. Yeah. Or you could have just do pi by diameter. I mean, it's a multiple equation. So that'd be 15 centimeters by pi. Because 2r is the diameter. So you gotta do that too. Alright? So that's how they get the A. So pi r squared, you get A. And you just get the L. So you just plug here L into the equation. You plug it A. Since it's a plastic, it have no relative permeability because it's not a ferromagnetic material. So it have no mu r. So it just be R is equal to ln mu 0 by E. Yeah? And you get your answer. Once you get your answer, now we have R. So since you have R now, you just make phi the subject of the formula. Let's talk about it on top there. Plug in N, you plug in your I, and you plug in the R that you just got. And just like that, when you substitute, get your answer. Yeah, and that's all it is. Nothing new. All right, nothing new. Okay, all it is. Everything else should be familiar. Everything at the analysis I did there is same thing. Because once you understand, you look at the center, the flux, which is center, you will know. Because it will give you the outer diameter and the inner one. Yeah? When I give you the diameter, it's always reference to the center of the material, right? So let's say the inner one is from here to here. Let's say outer is from here to the outer piece. Yeah? So just be careful when they give you the units. All right. Let's see what the question might be. Right. Well, if I talk about magnets, so I should be able to piece that together, right? Right, PHQ. Right, 29. Coercive force, right? The term is used to describe the value of the magnetic field intensity required to remove all the flux density. Well, yeah. So like the point of coercivity. right? So that's like before when we had it going up here and it came back. So this is retentivity. And when it goes back to zero here, this point is called the cohesive point or the cohesive force. It's basically the amount of H needed and by extension the amount of current needed to remove all the flux in the material. And because we know it lags, you will need a value for H to get B to the zero. Yeah, they don't go to zero at the same time. They'll lag, one lags the other one. So when he reach here, this B, they will need to continue to decrease H to get the B to be zero after a period of time. So that phenomenon to remove all the flux is the cohesive force. Yeah? Right. The integration of the total flux density passing through a closed loop will lead it. What? No. Heck. That makes any sense. The integration of the flux density passing through a closed loop will yield the energy. Yeah, it wouldn't give the field intensity. That'll make any sense. All right. All right. The next question, right? So 549 turns for dimension L and X. Okay. So this one you had to actually like do the calculations. They give you L and X uniform. They gave you H. They gave you this. So it's a magnetic material. Calculate the length of the air gap if the current is 3.7. Okay. Right. So they gave you some stuff. Always remember in the BH curve, if they give you H, you automatically have B. If they give you the type of material, right? So just keep that in the back of your mind, right? So that's in case he give you a question, he give you a BH curve, and he tell you it's a cast iron, and he give you H, and he probably busting up your brain like, but how I could find B already had the BH curve? Yeah? So once you have a BH curve and he give you a H, and he says cast iron, you can just go on the graph and just extrapolate it and get a B. Yeah, so never get confused by that. But that is assuming you give you the type of material. Yeah. Anyway. All right, so analyzing this is what I say X is for. And you say L is 94, right? So there's 94, there's 94, 94, 90. Yeah. So what I want. So what the length of the air gap, right? So this material here, I can't use Ampere circuit law of the job, right? So I need to manipulate the law a little bit. I think I did a question similar to this already. It's just that I asked it for a different value. Okay, so yes, I know they give you the values in centimeters, but for now I just working with the centimeters. In the exam, please convert it to meters. Yeah. So if I want the length, I could just say HL is equal to N, right? Flat off, good. So I need to break up this. Why I need to break up this? Because as I showed you all that thing last week, the reluctance to go through this air gap is extremely large. Yeah. So because of that, it's now 1H and it's now 1L. So you need to split them up. Think of it like having two resistors in a circuit, each resistor being different. So you have to find the sum of the resistance by the current and then add the both of them together to get the total current, or the total mmf or voltage, or whatever you want to call it. Yeah, remember Ni is F. All right. So this one you can say Hg Lg plus Hc Lc. Lc is for core, G is for gap, right? Is equal to Ni, right? Because I gave you I already and I gave you M. Yeah? Anytime they give you a current and it have a air gap, that basically telling you the amount of current I need to go to the core, and by extension, that air gap is 3.75. Yeah? And we know the B, just like I told you, is the same. So if they give you the flux density, that's the same of the material. Okay, so just like I showed you in the last couple of videos, just keep it in mind, right? So we have a nice equation to work with. They already gave you the H for the core. Yeah? So we need to find the LC for it, right? So to find LC, we need to pick a start. Say we can start with, let's say we start here, right? So this 4 here, let's break it up one time, right? I know it going through half of that. So basically from here to here is 2, 6. So same thing from on this side here. That's the same material. From here to here is 2. Same thing from the bottom here. From here to here is 2. And same thing 2. And same thing at the top. Yeah, because the material is symmetric, right? Or uniform as in opposite. Yeah, so now I can clearly see. So because of that, this 94 here, we can manipulate this 94, right? So we know on the top piece from here to here is 94, right? Yeah. So we could kind of manipulate this here to get LC. We could either write the L in terms of the gap, or we can write the gap in terms of the L. What I mean by that is if I want LC, LC will be, there's not 94. So you have to subtract this 2 on top here. Yeah. And you have to subtract this 2 on top here. So 94 minus 4, we are 90. So basically from here to here is 90. Okay, subtract the 2 from the ends I have. So, and then you have an A gap. Yeah? So the line is, the piece itself will just be 90 minus, we could just say LG for short. Yeah? So that is the piece with the A gap. So you have 2 of those pieces, right? So that means you have 2 of those to multiply by 2. Yeah? And then for the top piece now, it have no A gap, so it's just 90. It has subtract the 2 pieces that are being cut off by the edges. So 94 minus 2 plus 2, you get 90. So just 90 on top here. And you have another piece of, so it's 90 by 2. Yeah? So putting it all together now, you will have 180 minus your 2 length of the A gap. And you have plus a 180 again. And once you add those two together, you will get like 360 minus 2LG. Yeah, and that'll be the total length of the parts. So that'll basically be a LC. Yeah? So it'll be 360 minus the lengths of the air gaps on both sides. Yeah? And what LG is just LG. Okay? That's how you get the LC part. Right? So that's how you will normally destruct the question to get way out. Right? So there's a nice question to do. Right? So I go through the solution now, right? Right, so that's like I told you, you could get the F, or you can just use NI, like get the same answer, right? So in this case, I just calculate the F one time. Yeah, like get the same answer, because N by N, I is F, right? Because you know with the core, that means you have mu, so you have to multiply the mu 0 by mu R to get what mu is. Yeah, so I just doing the little pieces, piece by piece, right? So I get mu, and because you have your H, and you just calculating mu, you have this B you could get here, Tesla, right? And because the same B will be going through the core and the air gap, we could use this to basically finish the question. Once you remember, once you calculate the B, the same fluency will flow through the core and the air gap. You remember that, right? So that B now, if I want to calculate the H for the air, because we need that value, B is equal to mu H. We know this is free space air. And because we know B is the same as this here, we just divide it, so I make the H for the air. Yeah? And basically, that's what I did here, right? So 4L minus 2L. So the L is basically the 94. So basically, they did the entire length and just subtract the 2L. Yeah, so you could do that if you want. If you're not seeing that mass there, just forget about it. Go back to the shape, break down each piece. Just remember going to the center, and you get your value, and just minus the 2L from that. Yeah? If you're not strong in maths, don't let stress you out. Please, don't let stress you. All right? All right. So now FT is equal to F at the core plus F at the A. That's like a 2, right? So HLC plus H2LG. Why is 2? Because there's 2 air gaps. Yeah, and they subtracted the air gap from the LC already. So this LC is literally just core. And this 2LG is the air gap. So you have to separate it, right? So you just do the same thing. HLC LC specifically because the sub the length of the air gaps plus H of the gap plus 2LG. And once you do your maths and you solve, you'll get your answer. All right. This part here might be the confusing part, but if you're not seeing that, just calculate it by half. Just like I show you all with this here. Yeah, just do like that. Calculate each piece separately, add them up, and just subtract the two air gaps. So that'll be minus 2 Lg from the LC. Yeah, because the core and the air gap is two different things, right? Yeah, that's separate. All right, last question. When applying the field intensity H to the material, the point at which the domains cannot move much and the magnetic moments are almost fully aligned. Yeah, that is saturation. Yeah, remember the BH. As you continue to increase H, the B will saturate. And just like I told you, that saturation is caused by all the magnetic domains being aligned in the same direction. At that point, your B cannot increase anymore. So it will just saturate. So no matter how much you increase your current, you can't get any more flux density out of the core. Right? With that said, that is the end of the midterm. I will advise you all to try this question because this is a nice question to do to make sure you master the skills, especially calculating the lengths. Yeah, try the question, breaking it down with the air gaps, the B, things I'm telling you to keep in mind, and you should be able to be good. Yeah, once you understand the BH curve, the hysteresis loop, eddy currents, skin effect, I show you all fringing, I show you all the coils, I show you all the questions, which should be redundant by now. Yeah, and I show you all this one, I show you all the bulging, I show you all that, so you all should be good. All right, so my advice to you all is to review the video, redo the question, especially the calculation type questions, do the questions, the theory questions, go through the midterm, do more research on yourself, make sure you understand it, down pat, and you should be good for your exam. All right, so let's stop the recording there.